Yeah, thank you very much, Igor, for your work, and also, of course, to Reza for providing the funding. I have to say that science has a tradition of having important workshops because I couldn't help thinking when Igor was saying about that workshop that um, the modern story of numerical for simulation of the atmosphere of the ocean actually started with another workshop that was made in the late 40s in Princeton when John von Neumann, that is a recurrent figure in our discussion, held a workshop to try to convince a number of people, both at the agencies and in the academic community, to actually fund this project to make electronic calculators. And I read the proposal that Jules Charney wrote, and he said that in that proposal that they really needed a machine that could make a multiplication in 3-4 milliseconds, he said, because that was much faster than 3-4 seconds that the mechanical machine were actually achieving at that time. But I really love that proposal for the sharpness of the program, in the sense that they knew exactly what kind of resources were required for the task they have in mind. And I have to say that's something that we are a little bit lost along the lines, because the community has often operated on a mode of give us the biggest machine you can, we'll do something with it. That's exactly the opposite. Instead of saying, look, you should build a machine made like this, this, and this, so that we can solve this problem, we have been operating the other way around, and I think that's not really a way science innovation should go. Okay, sorry for the little spiel, and let's try to concentrate on the discussion. And this is more than a discussion. This is probably a story, and basically the story is why we got interest in the Koopman theory. And as I said, this is linked with the development of our field. Everybody knows about Richardson, that he wrote actually about 100 years ago. This book that was called Numerical Weather by, Weather Forecast by Numerical Process, 1992. It's full of folklore. He wrote the book while driving ambulances on the Western Front in France. He was a conscience objector. He was a Quaker. That's why he was driving ambulances rather than fighting. So this book is pretty amazing specimen, actually. It's describing in detail how to use numerical methods to solve partial differential equations. In specific, of course, there was the Navier-Stokes equation applied to the atmosphere plus thermodynamics, the full set that we now call primitive equations. So he did that, and if you read that book, you'll find out that what we have been doing the last 100 years is basically been realizing Richardson vision. In a way, conceptually, there is nothing more to what we have done. We have basically made that vision possible. We have expanded it. We have articulated. We have included the ocean, the ice, sea ice, the land ice, the ecosystems. But if you look at it carefully, you can trace the intellectual roots of what we do in that book. And so he did all this, and that's what we've been doing. And for all the past decades, we have been driven to create this numerical forecast system that is based on time marching circulation. Forecast means that you have to take great care of the initial condition preparation. All the information is the initial condition. That's the more or less explicit paradigm. So if you have a very good initial condition, of course you need a very good model. This means fidelity. It must be a model that represents the real process there. So you need a very good initial condition. This means you need to develop methods to create good initial conditions. So the whole field of data simulation was basically created, in which we are mixing observations constrained by initially, they were constrained by static constraints. So we want them to be hydrostatic. We want them to be in geostrophic balance. But slowly, we realized that the place in which we have put all the constraints we know is the model. So data simulation is constrained by model evolution, and these are the modern system of data assimilation. So skill is a direct function of the accuracy of the initial condition. But that, more or less halfway, it was discovered that this picture has some drawbacks. It's very sensitive to that same initial condition. You know, Ed Lorenz's work have been quoted, you know the story. But this prompted the different development. Then people start to discuss that the forecast cannot really be a single forecast because of the uncertainty that is anyway encoded into the initial condition. So limits of predictability were developed. You know, the whole field of science, you know, predictability studies was created, and people were, you know, trying to investigate how predictability limits were, in which way they were function of the property of the fluid, and so on. This developed this prompt development of ensembles approaches. So now modern forecasts are never a single forecast. There are a bunch of them, in which we try to sample the uncertainty and basically give an idea of what is the intrinsic variability due to sensitivity to initial condition. So that's the state of the art. But of course, conceptually, this is a big change because we're moving from a vision in which we're trying basically to predict a trajectory to a vision where we're trying to actually grasp and identify a probability distribution. So operationally is very simple. Instead of one forecast, you run 15 or 20 or 50 or whatever. But conceptually is a big change. And the way in which we're doing that is very clumsy. We're basically trying to sample an unknown, potentially huge probability distribution by making a very limited number of samples. Even if you make, you know, modern system make maybe 100 forecasts every day for the next 10 days, there's no way enough to actually sample the real probability distribution, what we think is the atmospheric probability distribution, right? So we were guessing. So the motivation that we started to think a few years ago was, well, but why don't we go after directly the probability distribution? Why don't we go try to use some of the methods that have been developed to actually try to predict the evolution of the probability distribution? And so together with a friend of mine, probably you know, Joe Tribia, we tried to use some of the techniques developed in stochastic method to go after the probability distribution. So Fokker-Planck methods, path integrals, you know, try to do. Of course, we were sort of stuck with really low number of degrees of freedom. So it looked like a dead end. Until I found out Koopman operators. But at that stage, what was most interesting for me was the adjoint. The Perron-Frobenius operator that actually is propagating the probability distribution. So in a way, we arrive at this problem by looking at the chance that we got a way of estimating the probability distribution evolution without having to do ensembles in some clumsy way. So that's what we did. And this is the Koopman operators. I don't need to repeat the definition that has been done in much better ways by many other people. So our idea was to try to look at both things, both the Koopman operator and its adjoint, the Perron-Frobenius, with the idea that maybe we could get a way of being able to predict the evolution of the probability distribution itself. And of course, this is the decomposition. You know, we're meteorologists, so we assume that everything is nice, that there are no problems. So we look at these formulas and we think, oh yeah, we understand. There are subtle things going on, but actually we don't care. And so we sort of move forward. And we decided to use the scheme that Stefan had devised to estimate the Koopman decomposition from data. And that's basically what we did. So we used the kernel extended dynamical mode decomposition that he has developed. And also we found that in a way, one version of this was already being used by the meteorological community for a long time. In fact, if you use a linear kernel in its formulation, that is equivalent to linear inverse methods that have been in use in the community for a long time. This is another case of things being rediscovered many times. So this was a good starting point because it allowed us to get a contact with the community. Of course, it was also an issue because then the problem was, is this really better, that much simpler limb that we know very well and it works very well, it's semi-operational and NOAA, and what's the sensitivity? So I'll tell you in a moment. What happened was that those things we brush under the carpet by saying we don't care. Actually, we have to care about that because then they generate sensitivity, and I'll show you in a moment in the calculation. Okay, so we create the gram matrices and, you know, with the kernel and everything, and this is Stefan results that we use in order to get the decomposition. And of course, it was very appealing to us because those axes that you see there are, you will see in a moment, are the sea surface temperature distribution over the entire globe in some cases, or over the tropics, but rarely their length is less than 60,000. So we have 60,000 grid point in one vector, and Stefan approach with the gram matrices is particularly appealing because then we have to do it the other way around, so we get that in time, so we get much manageable matrices, and without that approach, we couldn't really solve this problem. In fact, one of the discussion with the limb community is that the limb community had to basically use space reduction techniques by doing a preliminary PCA decomposition and then limiting to some PCA because the original formulation of limb is in space, so their matrices are limited by the number of spatial degrees of freedom. So they couldn't do it in grid point space, so just to be clear. In fact, we can, and in some experiments, we have shown that we get exactly the same results if we do this calculation in the grid point space or in a PCA space where we take all the components. So it's pretty powerful and it works. Of course, then we get all the composition as Stefan has shown in his presentation. And then, okay, well, which observables we concentrate? Well, we concentrate on the state itself because that's where the forecast is, even if we haven't really explored the full potential of looking at other observables that I think is there, but we simply have never done that because the comparison with the standard forecast has to be done on the state. We did the same thing for the adjoint. So we did the expansion of the probability distribution using the adjoint eigenfunction. Well, no, sorry, not eigenfunctions, whatever they are. And we tried to use this in order to see if we could predict probability evolution. So the first try was a one-dimensional case. What we tried to do was to take the Niño tree time series index, is a one-dimensional index of El Niño variability in the Pacific that is available for more than 100 years. And then we tried to use this technique to look at the possibility of creating a forecasting system for probability. Now, in one dimension, I can plot the probability distribution itself, and that's, let's see, is this? And that's what we see here are 6 cases of evolution. The blue one is the initial probability that was arbitrarily set to some spread. And then using the predictors computed with the adjoint of the operator, we actually look at the evolution over several cases. And we saw that there are asymmetries if you start with okay, this must be a cold case, and this is a warm case. And anyway, so this is the evolution of the probability. So you can do it in one dimension. And in this particular case, everything sort of tends to some asymptotic probability distribution. That's basically a climatological one. Then we try to apply that to the full SST field. And what we see here is a time series of coefficient. Well, what we did was that we did the preliminary PCA just for convenience. You don't, as I said, you don't need to do that. We could actually skip the whole thing. Basically for us, this PCA is a change of coordinates. Instead of using the grid point coordinates, I use the PCA. So I could use all the 600 PCA that I get. And so just for convenience, I show you this is the time series of the coefficient of the first 3 PCA. In this case, this is for the tropical zone, plus minus 35 degrees north-south. And with data is reconstruction that's done at the Hadley Center, the Met Office. So it's going from 80-70 to basically today, somewhere like that. So this is the kind of variability we get. These are monthly mean data, so we have a number every month for this period. And this is the spectra of the Koopman eigenvalues for that time series. They're mostly on the unit circle. There's something inside. And this is obtained with the kernel EDMD method with the Gaussian kernel. Of course, the kernel is sensitive to the bandwidth. So we played around with the bandwidth. We came up with the criteria by which we choose the bandwidth that makes the distance between all points equal to 1. So that's what you see here. It turns out that Dimitri published a paper in which he tried to use a bandwidth that was estimated by the state density with some Gaussian density calculation. We try to do the same. It turns out the actual number is not so different. So it does make a lot of difference if you use that particular thing. But of course, if you change a lot, things are sensitive. Now, as I said, we brush under the rug the whole issue of the continuous spectra that in fact is a serious issue. So we try to handle it somewhat. And one thing we did was we tried to compute, make a density estimation along the circle. So what you see here, these are density estimation along the circle. These are basically the density is done only on the angular variable, so only on the imaginary one. So if you want, what I'm doing is that I'm averaging on a wedge, starting from the center and going for a circle. And then this averaging is done. And then if you do that, you get this spectral, this density estimation. Now this has been translated in periods just to make life easier to people that read. So what happens is that the density of the eigenvalue is not uniform. There is like a sort of uniform band, but there are visible areas where the eigenvalue concentrate that creates peaks of density. And this is a bootstrap evaluation by changing stuff to try to see if by randomly rearranging the time series, we will get this by chance. Okay, so it's some poor estimation of reliability of these peaks. But to me, it's already remarkable that this concentration of eigenvalue exists. So in somewhat, they are describing areas that if that raise above the sea of eigenvalues. And if I have to think about it, that this frequency must be somewhat more important than the others. And of course, one is happy to see that these frequencies are way in the range of the El Niño variability. This is a decadal variability of the Pacific. So it's encouraging. And then, of course, we get all sorts of high frequency stuff here. And this is for the tropics. If I do that for the global, this is now the global SST, you can see the interannual peak is still there. The decadal peak has sort of shifted in a period, but nevertheless, just the existence of this peak is interesting. No, sea surface temperature. Yeah, sea surface temperature data, monthly data, so once a month. Resolution is 1 degree. So we have like, I don't know. As I said, here there are probably 64,000 points, and here there will be like 200,000, something like that. Oh, okay, this is how, this eigenfunction in time looks like. That's nothing special here. And this is the spectrum of modes. These are ordered in terms of their norm. So there are bigger ones and smaller ones. Now, looking at all these modes, we were stuck by the fact that some of the real part, some of them had a really small real part. So they were almost quasi-stationary. Now, then the question came, are these quasi-stationary modes privileged or different from the others? So we tried to look at the stationary modes. We had to find a criterion. And so the criterion was that we declared to be stationary anything that had growth rates of longer than 300 years, that for a time series under 40 years is sort of reasonable. Of course, you can play with that. That's totally arbitrary. But then if you look at the stationary modes, that's how they look like. And just by eye inspection, they look pretty stationary to me. But of course, we can discuss. Now, what shall we do with these stationary modes? Well, if they're special, they must have some special properties. And so what we try to see what happens if I try to reconstruct the Nino tree index by a selected reconstruction of the Koopman modes. So the thin black line are observations, and then the colored lines are different reconstruction by restricting to a subset of Koopman modes. For instance, the red line is basically, I'm using all the modes around a peak at 6 months. So I'm basically banding, I'm declaring that is a band of modes around 6 months, and then I'm taking only those. And then after the fact, I'm averaging to get the Nino 3-4 index that is an average over a box around the equator in the tropics. If you do that, you get the red line. And then I can repeat by taking the band at 12 months, and then I get the blue line. And then I can say, well, I'll tell you what, I'll take all the stationary modes, there are about 89 modes, and then I get the green line. And then I try to make the correlation with observation, and the stationary modes have a correlation 0.6 that is higher than the others. And I can tell you is higher than any correlation of arbitrary 89 modes takes at random, much higher. So it looks like if I have to speculate, the Nino tree is basically has a sort of a fundamental behavior given by the stationary modes, then they get amplified here and there by something. So the picture that emerges is that the texture of the variability is given by the stationary modes, and then something is creating local amplification. I will get back to this. Now, how these modes looks like? These are Koopman modes now, corresponding to various eigenvalues. This is the mode at 3.4 years that I show you. So, of course, this is a cycle. This is not a stationary mode. This is one that has a growth rate of about 5 years, just to give you a feeling. This is a stationary mode that is closer to that peak. So this is a stationary mode at 3.6, and this is much oscillatory. So they look like the modes that we can identify every once in a while. And then, of course, these are other frequency. 2.6 is a different one. There's a structure that's much closer to the South America. And this is instead the 9-year mode, stationary, as a structure that extends much farther into the mid-latitudes, much wider. So this is, the previous modes were mostly tropical modes. This one is, in fact, if I showed you the global one, it will show you that reaches in the entire Pacific. So we're sort of grasping a piece of this mode that is really extending. Because of the geographic selection, we're actually taking only one piece of this mode that is bigger. Oh, I will skip this. Okay, then of course I can construct predictors with the Koopman. And this was a preliminary analysis, and later Paula will speak much more in detail about predictions, but this is just to give an idea of what we can do by using, in this case, the Koopman operator. And this was a comparison between the polynomial, in this case is a linear kernel, and this is the Gaussian kernel, but I don't want to spend much time on this because Paula will discuss this in detail. But we also use the Perron-Frobenius operator to predict probability. Now, how can we describe probability of a system with 60,000 grid points, right? So the way we do it is that what we can do is that we can assume that in every grid point there is a variance, and then I take the evolution of the probability as the evolution of this variance. So I can use the Perron decomposition to start from arbitrary. You start from an initial condition, and then you stick at every grid point an arbitrary variance distribution. You stick a Gaussian in every grid point. And then you look at how these things evolves over time. In this case, what we see, these are all different initial conditions, and these are integrated. So these are the variants integrated over the entire domain. And the blue line is after 3 months. The red line is after 6 months. Everything started at variance 1. So what the rationale of showing this is I'm not getting always the same thing. So there are a lot. This shows that there is information. So the system is picking the information from the initial condition, combining with the Perron eigen decomposition, and then creating me different estimation of how the variance will evolve. So in some cases, the variance will go down. So in this particular case, they started at 1 here, and then the variance did actually the probability squeezed. In some other cases, it grew. And the nice thing is that this is an integrated measure, but I can also give you the spatial distribution. So I can give you what's happening when you start, say, this would be the variance distribution starting in March. This is after 3 months. And remember, this picture at the beginning was simply flat because everywhere was 1. So what it's telling me is that the variance is actually getting smaller in this area, bigger in this area, and this will give me an estimate of how my this is known in the business as the spread. And the spread is like the holy grail of all these things. People believe that if your forecasts have a smaller spread, they're more reliable. I'm not sure I agree with that, but that's the wisdom. So by looking at how the spread evolves, without having the need of making 25 zillions ensembles, I think is an interesting information. Let me finish then going back with those stationary modes. So are those stationary modes interesting? Well, what we see here are the scalar products between the eigenfunctions of the Koopman operator. They're ordered in a way that these are stationary modes, and here they're all the others. So what's happening is that the stationary modes are quasi-orthogonal among the others. That's in a way is to be expected. There is a cut of the sides, but you can see that they're not only quasi-orthogonal, but they define subgroups. So they tend to interact among themselves here and very little with this one. But then these are all the other modes, right? So these modes will interact with the stationary modes. So one way I like to think of this is that then the picture may be that the system evolves following the stationary modes, but there are interactions with the non-stationary ones. And that they create enough perturbation, then they create the amplification that we have seen in the Nino 3.4. So if one could come up with some perturbation theory in which one could take this part as a basis and then define the interaction with the non-stationary modes as perturbation, maybe we could try to come up with something that will allow us to give us the effective probability of amplification of these modes. And the stationary modes are nice because they tend to be basically Koopman restricted on this mode is unitary. You can do a lot of things if that's the case. So I think that in a way concentrating on the submanifold that's created by these modes and understanding the implication with the others is probably something that needs to be investigated better. And okay, this is just the other, okay, this was the global ocean and this was just the tropics, is the same spirit. So these are, of course, they're depending on the problem. So this, we have a different structure. Okay, just to conclude, well, guess what? It is possible to compute transfer operators from the kind of data we have at hand. That is not obviously needed. We can do linear predictors of nonlinear systems. We can do variance prediction, and we identify dynamically significant pattern. And maybe there is some hint that there are some more fundamental modes. So that's the end of the story, and in a way, it's not the end. I think we're at the beginning. I feel these methods are going to be very they open a host of possibilities that I think we need to investigate, as this was a very limited study based just on SSTs, on sea surface temperature. We haven't really investigated what happens if you do Koopman modes of the geopotential height at 500 millibars, for instance. So there is a whole multi-parametric studies that needs to be done. Anyway, thank you very much. Sorry, thank you.